don't you jump up there, yeah. All right, everybody. Thank you for coming to the first ever Improving JWST Data Products workshop. We're going to start with an opening statement from our director, Nancy Levinson, and then we'll go from there. Nancy?
All right. Terrific. So main point I've got to say is welcome. I'm really glad that all of you are here, that I hope that this is a collaborative and productive enterprise, that we share information, that we share knowledge, and ultimately that will put us all in a better place to continue doing the great science with JWST. And that is something to remark on, right? It has hardly been more than a year since we've been doing science and having science observations out of this amazing telescope. And the community, the global community, has been doing tremendous things with it so far. And so that's really rewarding. And we want to do even better. And that's what a lot of this is about. We've got this great new telescope with really complex instrumentation. Lots of different modes, lots of peculiarities of the various modes, and that's part of what we're trying to learn. The approach that we at Space Telescope Science Institute have taken overall has been to release the data, release the information. We have not held back with formal data releases, waiting until everything is all set. And what that means is that sometimes what you, the user community, have experienced has been a little bit rough, right? You might have gotten your data without the calibrations fully available or without the full sequence of the pipelines there. But that gives us an opportunity. We have released data products, which is a real range of things, including combined images, mosaicked images, IFU data, and so on. But I acknowledge that not everything has been immediately useful directly for science, and that's some of what we are trying to build on. And so I hope this workshop overall will really be a good learning experience for all of us as we get to share that information. And so I really appreciate those of you who are participating, whether you're here in the auditorium in Baltimore or whether you're online, because you have great knowledge about what you're trying to do, and you understand your science cases and what you've experienced. And so we at the Institute want to learn from you. And there's also learning we can do about your solutions and improvements. The pipelines are modular. They can be adjusted, or in some cases, you may even have wholesale revisions to things. And if those are things that we can incorporate into the pipelines or make available to others, then that should just help the science productivity overall out of this observatory. We also want to learn about your challenges. What have you run into that just plain doesn't work or that needs a fix? That's another piece of what we'll be talking about here. So really glad that you're here. These first couple of days will be, as Jeff had described it to me, a little bit of show and tell of let's just share information, what's out there, what are people doing. And I know some of you will be staying on for the subsequent 2 days where there will be a chance for some more hands-on exploration. So again, very much welcome to Space Telescope. I'm not going to be able to join you for this, but I'm really looking forward to hearing what the outcomes are and finding ways that we can all continue to do great science with JWST together. So thanks for being here.
Marco, could you help me? I am not qualified, not trained to get my presentation up. Thank you, Nancy. That was great. Great motivation for the workshop here. I'm going to give a few logistics. I guess I will stand over here. Okay, I'll give it a try. Yeah, look at that. All right, I'm Jeff Valenti, JWST mission scientist. So 5 slides here just to get us going. What's the goal of the workshop? We want to discuss ways to improve JWST data products and tools. Data products is the first bit. Tools is also important. Ideally, we'd love to provide science-ready data products to everybody through MAST, but alternatively, we want to enable a subset of researchers to reprocess their data. Not everybody can reprocess data. That's why we prefer to get the products in MAST as good as possible, but sometimes that's not possible for various reasons. And then provide general tools to help people analyze data products. Nobody can provide all the tools everybody needs to do all the science cases, but there are some cases where it makes sense to provide tools. So what is possible in principle to accomplish these goals and what is actually practical? That's what I want to get out. That's what we want to get out of this meeting. So anything that you can tell us to help us make those decisions, we want to hear. All right? That's the goal. This is not a training event, especially for those online hoping they're tuning in.
Recording has started.
Hoping they're tuning. For those online, this is not a training event. We do have JWebinars. We have a link that is updated as each new JWebinar is announced. There is one that's open now, JWebinar number 28, pipeline reprocessing of IFU spectroscopy, and there are announcements that go out on the Observer News when there's a new one. So for those of you looking for training, that's the best venue that has the broadest reach. Format, as Nancy described, we have 2 days of plenary talks starting now. The speakers in the auditorium are here with us, or they're online. We have a mixture of both. Those online are connecting, registered people online are connecting via BlueJeans. We will do questions and discussion via Slack. We will only bubble those up to real life discussions here if there's a little time at the end of a talk. But otherwise, and even if that occurs, the discussion is going to be too extensive, I hope, to do it in person. So we have the Slack. The address is here if you haven't logged into the Slack thing yet. We also have a free webcast, so people that aren't registered can watch, but they don't have access to the Slack, and so they don't have a way to monitor or contribute to the discussion. Then there'll be the 2 days of topical sessions, Thursday and Friday. There'll be plenary sessions right at the beginning and end of Monday, so we just make sure we know what we're doing and figure out what we did. And on Friday 1 to 2, we won't necessarily end Friday at 2, but people will start evaporating, so we want to have at least the final discussion there at 1 to 2. There's some 3-hour time slots. There's emails and Slack organization going on about all of that even now as we speak. There's refreshments for those who paid the in-person registration fee. That, for example, does not include me, so I brought my own. Locals hopefully brought their own. And if you need help, you've all seen the support desk out front. There's me, Jeff Valenti, and there's Marco here. Just ask us questions. Presenters, so this is really important. We need to have your talk emailed to the link that you were sent. It was in an attachment. It's also in the general channel of the Slack right now. This link, it's also on this slide, although I don't think you can type it fast enough. And we need it before the break, before your talk, at the absolute latest, because we need to go down here in order to load it on the laptop here without interfering with the presentations. If that's an issue, come talk to Marco or me, and we'll rearrange the schedule or something. I mean, that's really the only choice. Wear these mics, because although this mic is live, it just doesn't work reliably when you're looking at your slides and looking back. We have 2 of them. The next speaker, who will be Howard, please queue up as we're, not yet, but almost, sorry, let me rephrase that. As I'm nearing the end of my talk, please queue up, so, and similarly. Virtual speakers, you have some homework to do as well, not just uploading your talks, but you have to use the BlueJeans application, and you have to authorize BlueJeans to access your audio and your video. If you have a Mac, you've experienced this with lots of applications. Please do that before you're about to present. You can connect during the breaks to the BlueJeans instance and try sharing your screen then and deal with the pop-ups then without interfering with what's going on. Don't do it during the sessions, please. All right. Back to Slack, because this is different than normal. So here's the Slack address again. If you haven't registered for that, logged into that yet, please do, because it's going to be the heart of how we interact during this meeting. We're going to have presentations, but the interaction in these first 2 days is going to be in Slack. There are channels, like day 1, section 1 is the relevant one for this coming session. There's 4 sections per day divided by breaks and lunch. So we're mostly going to be listening to people because I want to hear from as many people as possible. That was the plan, hear from as many people as possible. Normally it's rude to sit in front of your computer and type during a talk, but not here. The goal here is to, if you have a question, just type it in the Slack, preferably at the speaker so that they can find it. And if you want to contribute to that discussion, to that particular question thread, ideally reply in thread. If you use Slack, you will know how to do that. If you don't worry about it. Just use Slack, all right? I mean, nothing's going to break if you just get your comments in there somehow. And then in the third, and the fourth days, we're going to have topic channels, like topic wide field spectroscopy and so forth. In preparing, days 3 and 4, we'll have some comparisons between the STSCI pipeline, ideally the latest one with the latest calibration data, but whatever, some version of that, and stuff that you all are providing in terms of alternate data products or code or whatever. If during this workshop you want to know, like, how do I run a single step, or how do I make it output something after this step, or whatever, we created a channel, Ask How to Do X with the pipeline. So just put the comment in there. We have a bunch of staff that are monitoring the event, that are monitoring Slack, that are here in the room. And so you'll probably get the fastest, well, the help desk is pretty fast, but you should get a fast answer if you put a question in there. It is our intention to lift, the Slack instance is only going to last 1 week after the meeting. It's our intention to lift the useful questions and comments as a record for people to go along with your talks. I will do some editing to make sure that it's all reasonable stuff from my perspective to be put out there. So just be aware. For Slack, don't be shy. Type stuff in there, all right? But do be polite, because I have a really thick skin, so I sometimes don't notice, but I can imagine that people might get into, your thing sucks, my thing's better, my thing's really okay, whatever. Just put that all aside. Let's just be polite. We're all on the same team. All right, I put the Slack link again here because I want everybody to log into Slack. So in case you missed it on the last slide or the first slide. The website has the schedule. There's paper copies out front. And then these links below are just for posterity, people looking at the slides. I don't think you'll need them here, but we have the JWebinars. There's a known issues page where we try to capture the known issues. We were not doing a good job of communicating what we knew about known issues and what our plan was to mitigate it. So a couple months ago, 3 months ago, 3 months ago, I guess, we published this page and we try to maintain it. If there's things on there things that are still issues that are not on that page, please email the help desk. Please email me if you are for some reason averse to emailing the help desk. But you're guaranteed of getting help if you getting it taken care of. You mail the help desk. We have a new calibration uncertainty page, which is trying to lay out top level what the uncertainties are. And there's a new JWST search interface in MAST, which is easier in many respects than the MAST portal, which continues to have functionality that we will maintain. So that's it for me. Howard, if you could, sorry, I didn't give a warning. Yes, Harry.
How to do X with pipeline, maybe how to do X that doesn't have to be with the pipeline.
Right, so Harry asks us to add a how to do X that does not involve the pipeline, and we will add that channel, that's fine, yeah. Yep, Drake? How do we get on the guest Wi-Fi? Good question. So I'm not going to say it out loud, but the network is ST guest, and the password is being whispered to you by somebody nearby you, maybe? Yes, thank you very much. The first 5 letters are capitalized. Any other questions? Oh, yeah, a little logistics here. There's a clock here for the speakers in the room. They're going to set a good example for the people that are online and can't see the clock. I'm going to be fairly ruthless. I learned when I was refereeing basketball that if you don't call the fouls at the beginning of the game, the quality of the game goes down. Right? So I'm going to call the fouls early, and we're going to cut people off so that we stay on schedule, and then the later speakers will know that they have to, if they want to show their last slides, they got to get it done. So, all right. And I'm going to, you want it back for the other people. All right, so that's it.
I have to wait for the clock to start. Okay. All right, well, welcome everyone. Good morning. This talk will actually be kind of a tag team between this one and the next one you're going to hear following myself, presented by James Davies, who, by the way, used to be one of our own in-house developers before he defected to elsewhere. But in my talk, I'm just going to give you kind of a high-level overview of the design and the way the calibration pipeline software is laid out, in case you haven't already figured it out in trying to do some of your own work on, customizing your own software and so on to fit into the pipeline. And then James is going to show a few more specific examples of how to do customization. So, as a quick reminder, I'm sure you're all well aware by now, it's not just a single calibration pipeline that we have. It's actually many pipeline modules that are split into various stages of calibration, starting with the low-level detector corrections and migrating into more and more unique areas applied to imaging versus spectroscopy, and then on to even higher level unique processing modes for things like coronography and time series and so on. So overall, as again, you're probably already aware, the calibration software is hosted in the public JWST repository out on GitHub. Code is pretty much 90% Python with some C extensions thrown in here and there for routines that need a lot of number crunching speed. Originally, all of the software for the pipeline was in that one repository, but then over the years, it's been split out into some parallel repositories just to make it easier to share common code amongst multiple observatories. In particular, at least here at the Institute, we do that so that the Roman calibration pipeline can share some of the infrastructure and so on with JWST. So some of those other parallel repos that are out there are first the ST pipe repo. This contains all the infrastructure and environment for just running the steps and pipelines and taking care of a high-level environment like that. I'm going to give some more details on each of these in subsequent slides. Then the ST data models package, which is where all of our software data models live. As I'll explain a little more in a minute, we tried to avoid any direct I/O in any of the pipeline steps that have to know anything about the data file formats and so on. And so that's all abstracted into software data models instead. And then there's the ST Cal package that it was created as well to house some common steps that are used by both JWST and Roman, things that are pretty much the same for both observatories, common things like saturation flagging, linearity correction, and so on. So there are half a dozen or so of those common steps that live in that STCal package. And I'm sure, as you're all aware, all the pipelines and steps can be run from the command line as well as from within a Python shell or a notebook environment and so on. We tried to make the JWST pipelines as modular and flexible as possible, as opposed to, say, some earlier generations of some of the HST pipelines, just so that everyone like yourselves can as easily as possible manipulate things and customize things to get it to work the best as you can on your own data. So the ST pipe package, yeah, as I mentioned, this manages all of the pipeline and step processes within each pipeline. It provides some common parameters or arguments that are available to all steps and pipelines. I list a few of them here on the slide, a few parameters that give you the ability to tell it to skip or not skip a step, or to save results coming out of a particular step. There are parameters available that allow you to override the reference file being used by a given step instead of automatically retrieving it from the calibration reference data system, and so on. And then, of course, each individual step can have its own unique parameters as well. So yeah, STPipe handles all the parameter parsing, file management, passing data from one step to another within the pipelines, the interface to CRDS for retrieving reference files, and so on. The ST data models package, as I mentioned, is there to support actual file I/O for all the steps and pipelines. We try to keep the knowledge of the actual file formats and their contents at arm's length from the software itself, so that, for example, if you're writing a correction step, you don't need to know what the FITS extension name is of the data array you're looking for, and so on. The data models abstracts all of that away from the step level software, and so you just then access things via attributes within the data models themselves that are returned to you. And this also makes it possible to just use different file formats throughout the pipeline. Most of the science products are in FITS format, but we do have some reference files that are in the ASDIF format, Advanced Scientific Data Format. And so again, by having these software data models, you don't have to know or care what format a particular file is in. You just say datamodels.open, and it'll open it and load it for you, regardless of what the format is. So yeah, this handles all of the low-level I/O interfaces to the actual FITS and ASDIF software libraries that are doing the low-level I/O ultimately. The data models are defined by schemas that are written in the fabulous YAML format. I'll show you an example of that in just a second. And another nice feature of this is because there is a defined schema for each data model, it allows a file to be validated both upon reading and writing it back out again. It's compared against the definitions in the schemas, and if it finds anything that doesn't match, it lets you know that this is not a valid file format. There's something wrong here. So a quick example, I hope this isn't too small to read. On the left there is just a little snippet of one schema for one of our data model types. That portion on the left defines the actual data arrays that are available within the model, defining as much as you want about them, their data type, their dimensions, and so on. It also contains a pointer to the name of the FITS extension if it's stored as a FITS file, so that the lower level software knows where to go to find it. And then on the right side is equivalent schema for metadata, aka FITS keywords. And there too, you can define properties for each of the pieces of metadata that give things like its data type, the comment field that appears with the keyword if it's stored in a FITS file, and so on. And just a quick example of some of these in use. Once you've imported the data models package, you can just very easily call datamodels.open, give it the name of the file you want to load, and you get an object back in Python, and you can then access all the various attributes of that. The main data array, sometimes referred to as the science image, has the obvious attribute name of data, very clever. And then you can access the whole meta attribute tree as well, which is stored in like a hierarchical fashion. We group certain types of metadata under different sections like instrument or exposure and so on. So you've got access to all of those pieces of metadata there in the model. And if you've made updates to it, you can then very easily save the updated model back out to a FITS file just using the save method on the data model. So now getting into a little more detail, just going to show you some of the fundamental pieces that are involved in a calibration step and why they're there and what they do. Here's just a trivial example that I borrowed from the linearity correction step. This isn't an exact copy of it, but it at least shows you a template of the structure of it. So you've got your linearity step class defined there, and it inherits from the step class that's defined in stpipe. There's a class alias that can be specified, which just acts as a shortcut or nickname for the step, so that like if you're running from the command line, you don't have to type JWST.linearity step, to access this particular step class. You can just type linearity and it knows what you're talking about. The next line down there, reference file types. This can be a list of one or more names of reference file types that the step needs. This is there so that when the step is first instantiated, it'll go off and do a prefetch or look in the CRDS system to find out, okay, is there a suitable linearity reference file available that I can use for this? And if not, it'll throw a warning so you know that even before you've wasted time trying to run the step, that you don't have a reference file available to use for it. You can then define any unique parameters that you want or need for the step here in this spec block. See how you can use that to define parameters that are various data types, either string, float, whatever. You can define ones that have optional values, and of course all of them come with an available default value that gets used if the user doesn't specify an explicit value. And then it goes down into the actual process method for the step, which is continued here. So again, a few key pieces of a typical step. Obviously, first thing you need to do is load your input, your science file that you want to work with. Just load that into a data model. Next, we have to go get our reference file that we want to use within the step. The get reference file method, again, is a common method that's available or defined in the step class. And that, again, calls the CRDS interface to find the name of the appropriate reference file to use. It passes that name back to you, which you can then go ahead and open again into another data model, and then go do what you need to do to actually apply the correction, just sending your reference file and input science model down to the actual correction routine. And then at the end, the corrected data model, which here I've called result, is just passed back up to ST pipe. And at that point, ST pipe does with it whatever it's been told to do with it. If you're running the step standalone, it'll just save that result out to a new file on disk. If it's within a pipeline, it'll pass the result in memory to the next step of the pipeline, and so on. Okay, so switching gears now for a minute to the concept of associations. Again, probably well aware of this if you've worked with the data at all. We use association files as inputs to some of the pipelines where the pipeline needs more than one input image or file for any reason. For example, in the stage 2 pipelines where you might want to do background subtraction or subtraction of near spec leak cal, or sometimes they're called imprint exposures, the association file is used to list the names of those different inputs that you need. And obviously, same thing in the stage 3 pipelines where you're trying to, say, combine a bunch of dithered images, or in the case of a special mode like coronagraphic data where you've got both data of your science target and a PSF reference star. Those are all listed in the association file, and they've each got a unique type associated with them to tell the pipeline, I'm a science image, or I'm a PSF image, or I'm a background image, or whatever, so that it knows what to do with it. I see my clock running down, so I'm going to move through here a little fast. Here's just an example of how you can work with associations from within Python. You can actually load an entire association at once if you want. Again, the data models library knows how to handle an association file. So if you just call the open method and your input that you've supplied to it is recognized as being an association file, it first reads that association file to get the list of all the actual images you want to load, and then loads all of those images for you, so that the returned object that you get in Python is actually a list of all those data models that it loaded. And you can customize that to only load particular types of images from the association if you want. Here, an example, again, for coronagraphic data, where you only want to load the science and PSF images. And then you can do all sorts of manipulation with them based on those member types, however you want to do that. And then finally, I just want to briefly touch on how we handle world coordinate systems in the data products. We use the generalized world coordinate system library that's out there as part of part of AstroPy, or is it affiliated? Anyway, it's out there. We do not rely on the traditional FITS WCS information for doing processing. For imaging modes, we do at least store traditional FITS WCS keywords in the headers of the FITS files, but those are there purely for the purpose of backwards compatibility, such that if you just want to load an image up into DS9 or something, that you'll get some reasonable cursor feedback on what your RA and DEC are as you scan around the image. And for images that have not been rectified or drizzled, we use the FITS SIP convention to store, distortion coefficients as well. Okay, thanks. And then moving on for spectroscopic modes, because the spectroscopic modes are often so complicated, like for IFU data or near spec MOS data, it's virtually impossible to try to store anything physically reasonable for World Coordinate System information in any of the available FITS WCS conventions. So in order to not store bad information, we just don't store any FITS WCS information at all in spectroscopic data, and instead just rely entirely on the GWCS object that's stored within the files and the data models. And I just show a quick example here for an IFU image like the one you see on the right. There's an individual world coordinate system defined for each of those 30 slices of the IFU data that you see in the image. And so there are special routines within the pipeline software, you see in this example here, where you can load the list of WCS information first for all of the slices within a given image, and then you can pick out, say, one of those here. I've chosen the example of, well, let's look at the WCS associated with IFU slice 12. That's got a bounding box defined, that's isolated, you know, to slice number 12, wherever it sits within the image. And then the obvious detector to sky transforms are always available very easily to you. For example, in the forward direction, if you've got that WCS object for slice number 12 and you just give it a pair of XY image coordinates, it'll spit back RA, DEC, and lambda values for you. And then you can go the opposite direction as well, just by using the backward transform method, where you put in RA, DEC, and wavelength, and it returns X and Y to you. So, I think that's it.
Excellent, thank you.
So that was your full 20 minutes. So we're just going to do the discussion online. For future speakers, when I give the 2-minute warning, if the next speaker could come up to Marco and start miking up, that would be awesome. I have seeded the discussion in Slack. I'm feeling kind of lonely, so if the participants could chime in with questions, that would be awesome. James?
Thank you, Howard. Great to be here. Great to see familiar faces of friends and former colleagues. My name is James Davies. I'll be telling you a little bit more about the infrastructure. I spent 6 years here at Space Telescope developing calibration pipeline along with Howard and others. If you go to GitHub, that's the pulse at the very top of commits. It only starts at the beginning of 2017, but I think for 4 years previous to that, we were using SVN internally. But this gives you kind of an idea of the amount of work going into developing this pipeline. That's me. I committed code, but I deleted a lot more than I, so I don't know, on balance. Hopefully it was okay. In 2021, you can see my contributions abruptly end at the end of October, 2 months before launch. Was this, you hear me okay now? Is that okay? Good, thanks. Yeah, so my wife and I had a newborn and we moved to Germany for new jobs. So that's where I am now at the Max Planck Institute for Astronomy, and we are up to our ears in JWST data there. We've got lots of geo PIs there, even more COIs, 2 of which you'll probably be hearing about in later talks today and tomorrow. plus the GTO programs. We have members of the GTO teams there for both MIRI and NearSpec. MPIA built the filter wheel for MIRI and contributed to the hardware for NearSpec's GRISM wheel. And you can see the arrow there where that stuff was actually built in Heidelberg. So 6 months after launch, we all saw the ERS and ERO data, and we were chuffed. It was spectacular. We had a big hack day at MPIA, and a full day JWST hack day. It was a lot of fun. We looked at the data that was available. The first thing we looked at was this wonderful Q3D data, the ERS data. I've mislabeled it. And this is a single frame. A single detector. You're seeing groups, so this is 20 groups. This is accumulation of space weather, cosmic rays. But of course, the pipeline calibrates that, and you get something that kind of looks like a real bunch of real spectrum. I think I'm in the right room here where we can all get super excited about looking at an IFU slice image, right? This is amazing. This is like a redshift 3 quasar. It's spectacular. But you can see that, you know, there's like pock marks there still. And I think on that first day, we were, you know, we immediately started like, I think we pulled out Larry Bradley's implementation of Peter Van Doken's LA Cosmic and inserted it between Detector 1 pipeline and Spec 2 pipeline and tried to clean stuff up a bit. And then we quickly realized, no, we actually have to hack the pipelines themselves. It's a good thing, as Howard pointed out, that the pipelines are actually very hackable. They were designed that way. And so that's what I'm going to talk to you about today. Howard has already gone over details of the step class. The pipeline class is actually a subclass of steps. So it does everything steps does. It just kind of keeps track of some extra things. The process method, Howard already pointed out. This pre-hooks and post-hooks is like the killer app. And this is what I want. If you walk away from this talk with anything today, I want you to remember that. I'll briefly talk about ST-pipe and ST-run. And then if you're really into distributing your code, I'll talk about entry points. So a custom step, Howard already showed you this. This is the bare minimum for a step that will run with JWST data. We're shoveling pixels here in some random way, I'm not sure. But the important thing is that it has a name. I've subclassed step, and I have a class alias, and it has a process method. In this case, it takes your input data and just returns it back to you. That's not very interesting, so let's maybe read in the data. Here we're reading it in using data models, just as Howard showed. I'm making a copy right away. When you're running pipelines, if the pipeline fails, you don't want to be editing your input data. You want to be having a nice fail point. So we're making a copy, and then we're returning that. So still we're not doing anything. Let's actually do something. Let's insert an algorithm here. I'm really excited to hear about everyone's algorithms over the next few days, and I know there's some really good ones out there. And if you have a function that processes some JWST NumPy array, this is where you'd put it. So we can make another step, and you notice that, you know, shovel pixel step, the only thing that really changes are the names, but the basic design pattern is the same. So here's an example of an actual implemented one that I made. This gets rid of some of those snowballs we saw on that NearSpec IFU image. Again, we're subclassing step. We have some parameters that control how we work with the snowballs, and we have a class alias. I call it snowblind, and I snipped out all the algorithm, but it's another 20, 25 lines, and that's it. It's actually based off of the initial version of the snowball flagging that Gabe Brammer implemented in Grizzly, and has some enhancements. And I know Gabe has enhanced his as well too. But it's very simple. And at the end, we set an attribute that says it's complete, and we're done. So this is something you can actually you could put this code into an IPython, hit return, and now you have a step, and you could actually run it on JWST pipeline. You could run it on JWST data. we'll use this as an example for the rest of the talk. It's actually available on the MPIA GitHub org, and you can actually install it, just pip install Snowblind. And there's a couple other steps there too for handling frame averaged, group data, the jumps, and persistence, and a couple other things. But anyway, feel free to have a look at it or to talk to me later. But what does it do? Well, okay, I showed you the NRS1 detector before. This is the NRS2 detector of the exact same Q3D ERS data. And yeah, it cleans it up. It's nice. It's not too bad. So there's a bunch of algorithms that do this sort of cleaning of sort of, I feel like the low-hanging fruit for extracting signal to noise from JWST data is in the level 1 pipeline right now, because there's still a lot of effects that we still don't quite, haven't quite perfected. But it's getting better, and the JWST pipeline itself has gotten a lot better over the past year, and I think as reference files get sort of tuned better, things will converge. So in addition to writing custom steps, you could write a custom pipeline. So here I've made an imaginary module that has those 2 steps that we imagined earlier. I wrote something called my pipeline. The only difference between a pipeline and a step really is it has this dictionary called step-defs, which defines what steps are available in this pipeline. It uses the aliases for simplicity. So when this pipeline when I get an instance of this pipeline, it makes instances of all the steps as well. And then the only thing that the process method of a pipeline does is basically takes the input and runs it through each step sequentially. So the output from one step gets piped into the input of the next. And you can see that because I have step defs here, shovel pixels becomes self shovel pixels method in the step. So it's really simple. And in fact, the existing official pipelines are exactly that simple. I've clipped out some of the code here, but this is actually a snapshot of the existing detector 1 pipeline, and you can see it's got a class alias. There's some spec for some parameter. There's step defs. There's a lot more than this. I've just clipped them right there, so you can see that's the group scale step, and then a MIRI is handled different than near spec and the near IR detectors. I clipped out all the MIRI, sorry MIRI folks. The near IR, different ordering of the steps. And again, they're just called one after another, and then in the end, it returns a result. One thing you'll notice about these pipelines and steps is that we're not reading in any FITS files. We're not futzing around with any HDUs or any io.fits calls, and we're not writing anything out. So in addition to putting together your own pipeline with your own steps, you can write your own pipeline with some of the official steps. Say you have some rate files and maybe it's that same IFU data and you need to know where the light from the sky falls on the detector. If you need to know that, you actually need to have assign WCS run on it. So here we import the official assign WCS up at the top there. We add it to our pipeline, and then we run these other 2 steps, which we haven't really defined yet, but maybe they do something interesting. But they might depend on having a WCS available. Okay, so this is where it starts getting a little fun. These are the last steps of detector 1. And a lot of the, I think, early work in this past year has been hacking this pipeline to do stuff like maybe further up or further down, but generally right after jump step runs. And in this case, I'm going to show you how to, so jump step, right? The end of jump step is it updates the data quality array. You still have a cube showing all the groups of the data. And then ramp fit runs and fits slopes and gives you a 2D image. And you have thrown away a lot of the information after you've done the ramp fitting. So if you want to do any further like flagging or flagging of, say, of errant pixels, you need to do it somewhere here. And that's kind of what Snowblind does. It just flags pixels and this jump plus step, which handles some of the frame average data in a slightly different way. So I'm going to show you how you might insert these 2 steps into the official pipeline using pre-hooks and post-hooks. Pre-hooks and post-hooks are documented somewhere in our documentation of the pipeline, but I suspect no one has heard of them. So let's look at how you would do it. Here we're using detector1 pipeline call. We have some input data. And for the jump step, we're defining a post hook. Hooks are lists of strings currently. And the string contains the sort of fully qualified name of the step. In this case, it's the Snowblind package, which you can install, pip install Snowblind. And so it's Snowblind step, jump plus step. But say you had a Jupyter notebook and you had a little sidecar.py file called Snowblind, it could find it there as well. But it's just a string telling the hook where to find the step. If we run this, we get some log, and the log, well, there's a big long log. I've snipped out the relevant bits. At the jump step, when it's instantiating the step, jump, it defines something as .jump, .posthook0, posthook1, and you can see those are the steps. It's making instances of them, and if we continued looking at the log, it would actually run those steps. And then when they were done running, it would then run ramp fitting. So, that's great. It saves you a lot of time, a lot of effort in sort of hacking together your own pipelines. You can just use the existing infrastructure to insert your algorithms into the existing official pipeline. So there's some caveats here. Currently, pre-hooks and post-hooks only work properly when you use the call method. So call is basically it's a class instance factory. Basically, it takes your class, your detector1 pipeline, makes an instance of it, and runs it. And you need the data to start with. So it only works with call and the command line. If you're using .run, you're sort of out of luck. That said, we might be able to fix that in the near future, and maybe I'll work on that this week. Also, you currently can't pass step. So if I have a custom step that takes parameters, currently there's no good way you can pass step parameters to it when you use it as a pre-hook or post-hook. And that's a limitation. That kind of sucks. Again, that should be an easy fix as well. So these are things that I want to fix. Currently, if you do need to pass parameters, you can either write a custom pipeline, as we saw, or you can just use them as a single standalone step. And in those cases, you would pass parameters to them in the exact same way you do the official pipelines or official steps. But anyway, fixes for these are coming. I've been working on a PR, but it just hasn't happened yet. Howard briefly mentioned the command line interface. I'll just briefly mention it too. There are actually two command line two commands in the command line interface. One is called stpipe, and you can do stpipe list. This is actually really useful. It gives you a list of all the steps, their aliases, and all the pipelines. So all the pipelines are at the top here, all the steps are here, and at the bottom you'll notice it also lists my custom steps. That's cool. I get a free command line interface for my custom steps. And sure enough, if I do strun snowblind help, it lists all the standard parameters, and down at the bottom, those 4 custom parameters. So that's pretty cool too. And of course, I can actually run the pipeline, the Cal Web detector1 pipeline, with those post hooks on the command line as well, exactly the same as we did before. And it runs, and everything is successful. So this is useful. This is nice. I use this command line interface a lot to oftentimes get just the help of trying to remember what the interfaces are. And finally, just an example. This is some NearCam 4.7 micron narrowband imaging that we're working on right now at MPIA. This is a program PI'd by Eduardo Bernados, and I've been working on it with Janu Kusanova. And you can see that running both Snowblind and the Sears team's Ren striping code cleans the data really well. It's good. Now, this is not unique. There's a lot of algorithms that do the exact same thing out there. But the amount of code that I had to write to sort of do this was very minimal, as you can see sort of how in my approach. And finally, I'll just very briefly mention this. If you are thinking about distributing your code and you actually want to get the free command line interface, in your package setup, either in setup.py, setup.config, or in this case, PyProject.toml, you just identify this entry point. Entry points are Python's plugin architecture, and you just define all your steps, their aliases, and whether they're pipelines or not. I will leave you with my summary and mention that I'm here all week, and if anyone wants to turn their really cool algorithms into steps that you can use yourself, I'm happy to help. And if you want to get together and do like a hack during one of the sessions, I'd be up for that too. Thank you.
Awesome, thank you very much. The next speaker is online, so maybe you could start setting that up. We have some time for questions. I'm going to read from the questions online. You guys have not been very good at asking questions online. So does anybody, just as a test, does anybody have a question in real life that they just didn't feel like?
I feel like it, I just didn't remember I was supposed to do it.
Okay, good. So I invite you, since you're right in the front, come up and use the microphone so people can hear.
What's the advantage of a post hook or a pre hook compared to just adding a new step between the two steps?
So there's no advantage for, I think, people here at Space Telescope, because Space Telescope controls the official pipelines. But if at my scientific institution I want to do something in a very custom way, I may not want to rewrite the whole Detector 1 pipeline or even like make a copy of it. I just want to be able to on the fly insert a couple steps. And so that's kind of like that's the advantage. Yeah.
To be fair to the mass of people here, I don't control the pipeline either.
Yeah,
so
no,
it would probably be easier for me to do pre-hook and post-hook as well.
Yeah,
so.
yeah.
That's true for everybody. Okay, let's see. All right, we're going to keep our time. We're going to move on. Please do feel free to add questions.
I think you can grab the ball and just start sharing the screen.
All right, hello, can you hear me?
Yes, we can hear you a bit on the faint side.
Yeah, give me 1 second, I'll try to make it a bit louder. Your own custom Python scripts into something that looks like an official JWST step. So this is already something that's already proving to be quite useful for me. So I'm going to be talking a little bit about the work that we've been conducting at the University of Manchester in the UK. Sorry that couldn't be with you all today, but unfortunately the logistics meant I couldn't quite get to Baltimore in time for this conference. But what I'm going to be talking to you today is about what we're trying to do regarding to mass process public data as it gets released, with the main aim of trying to find high redshift galaxies in deep field data. And so we're kind of dubbing this the epoch sample. And so the idea is combine together multiple major observing programs together to form the largest collection of high redshift galaxies that we can. And I show here an example of a deep field image. This is the North Ecliptic Pole from the Pearl survey, or at least a quarter of the original field. I'm part of the Pearl's GTO team, so there may be a little bit of Pearl's bias if I show some images. But this is a project that's it's not just me. It's a group of people, mostly at the University of Manchester, that are working on this. And mostly early career researchers as well that are doing this. So it's postdocs and PhD students for the most part that are conducting this work. In particular, I'm going to shout out my two PhD students, Duncan Austin and Thomas Harvey, who've been doing a lot of work on the sort of second half of the pipeline that we've been making, which is kind of the post JWST imaging getting to the actual galaxy sample that we're after. And what I'm going to talk to you today is mostly about the first half of the pipeline we've been making, which is largely the NearCam pipeline that you're probably all relatively familiar with. And so what we have so far, or what we're trying to make, is a custom but consistent set of reductions for deep field surveys. We've seen teams like Sears, Primer, etc., all making their own reductions and producing their own pipelines for reducing their own data. And what we're trying to do is we're trying to have something that's consistent in terms of producing a set of reductions that implement some improvements with regards to background subtractions, wisp removals, these sort of problems, but apply to as much data as we possibly can. And so at the moment, we have about 180 square arc minutes of area processed in this pipeline to depths greater than about magnitude 28. And a sample at the minute, it stands around about 1,300 galaxies at redshift greater than 6.5. And the idea is that once we've conducted some initial projects with students on this, which should hopefully be done over this winter, we'll be releasing the catalogs and the images publicly. And probably with our second sort of data release that we're doing, we'll be releasing the code once we've tidied it up and documented it a bit. And so this is the sort of pipeline that we're following. So the idea is to try to condense all of this into a single bash script that you just press one button and let it run for a couple of days, and you get your nice clean JWST stage 3 images at the end of it. And so it will query MAST, run JWST stage 1, apply template-based WISP extraction. At the minute, we're using the most up-to-date WISP models that are on the Space Telescope website. But I'm going to talk to you a little bit more about this later in the talk, because that's the minute. This is probably the primary sticking point in some of our reductions. We run JWST stage 2, the 1/F correction devised by Chris Willett. We extract the background subtraction step in stage 2 and 3 and run it independently using plot utils. We found this just gave us a bit more playing room and was quicker for experimentation. We pulled this step out and played around with it a lot. JWST stage 3 is probably the second sticking point, because when you deal with some of the larger mosaics, say Cosmos Web, or trying to mosaic the entirety of Sears into one image, or the Jades images, the RAM usage for JWST stage 3 is pretty high. This has been improved. I would say thank you to people who have been improving the RAM usage in stage 3 to the point where we can run this on a 250 gig machine pretty much fine for all of the images that we're working with now. And then we're doing the usual sort of tidying up of the images afterwards. And the second half of the pipeline kind of goes from the images, the final data products, through to something that's ready for use for science. And so this is what our 2 PhD students are largely working on. So we've got automated image masking, which uses a Gaia catalog to use a template star mask, and it increases the size of the star mask as a function of the Gaia magnitude of these stars. Local depth calculations by placing empty apertures across your image, and then photometric redshifts and physical properties of galaxies using EASY, as well as bagpipes and Prospector. And we're also implementing simulated catalogs from Jaguar, which will also give you completeness and contamination rates for your whatever photo CE process that you're using. And at the end of this, what we're trying to get is a robust sample of high redshift galaxies. And so on the left-hand side here, I show an example of one of the plots that you get at the end of this pipeline, where this is one of the spectroscopically confirmed redshift 12 galaxies from the JADES program. And what we're seeing here is the orange line, you're seeing here is the main fit. The blue line is an example of a low redshift fit, and the green line is actually a brown dwarf star template. On the right-hand side here, we're actually showing a case where the brown dwarf star template is actually the better fitting solution to this. So not only are we getting catalogs of high redshift galaxies at the end of this, but we're also getting catalogs which may be interesting for different groups and different science cases, such as catalogs of brown dwarfs. One of the things that I mentioned is parallelization is one of the things that we're trying to build upon. And this sort of line in the middle here is a nice little bash script that will allow you to run multiple instances of the JWST pipeline, particularly stage 1 and stage 2, which are less intensive on the sort of RAM front. You can have 16 instances or however many CPU cores you have running at the same time using just this one little snippet of bash script code. And some of our custom Python scripts as well, we've written in a similar way, such that the Python code will take an argument from the command line as your input image. So the sort of pipeline that we have is just a simple bash script that you run that will search your folder full of uncal files and run stage 1, stage 2, and our custom Python bits in between on each of the images in there. And you just need to change, for example, your input file, if this is your stage 1 ASTA file or your stage 2 ASTA file or your Python script. And you can just change this P16 for however many CPU cores that you have. And so at the end of this, you kind of download your data, put it all in one folder and hit go. And after 4 days or so, you're sat with nice catalogs of the JADES field, for example. So this is the data release 1 from JADES. And I'm showing on the right-hand side depth maps from our pipeline relative to the official JADES pipeline. So I just downloaded the images from their data release, ran our local depth code on both of them to see what happens. And we'll find that we're on average, we're a little bit shallower, generally not too much, within 0.1 magnitudes across local depths across the images. The main sticker point, as I mentioned previously, and I'll mention it again in just a second, is wisping. You can see here the sort of larger red-yellow blob in this region is where wisp attraction is kind of not performing particularly well. But in terms of getting a reliable high redshift sample, this is something that seems to be performing relatively well. The high redshift galaxies found in Sears and JADES so far spectroscopically, we're picking up. I haven't updated this plot yet with Uncover, but we just reduced the Uncover program, enable 2744 cluster, and again, we're finding all of the high redshift galaxies spectroscopically confirmed there. Wisp attraction, as I mentioned, is a relatively big sticking point for us at the minute, and is something that I'm looking forward to hearing about. I've noticed some talks have wisps in their title already, so I'm looking forward to hearing what people have come up with for solving this. This is a little snippet of the newest JADES release, JADES DR2. And on the left-hand side, we have one of the inner NearCam blue modules, which are affected by wisps. On the right-hand side, we have one that's on the outer part of the NearCam module, which is not affected by wisps. And you can see the background is clearly worse, where there are regions where there's over-subtraction and under-subtraction in place. And so we've implemented a second two-dimensional background subtraction on the final images, and that works relatively well. I might bounce backwards and forwards between the two of these so you can kind of see the difference between them. But it's still the inner NearCam modules of the blue modules underperforming relative to the outer modules in terms of depth calculations at the end. So they're definitely still not there. And we generally find that this is a problem when you're dealing with images that are deeper, that are about magnitude 29.2 to 29.5-ish, is where just template-based wisp attraction isn't performing so well. And so there was a paper released by the group in Australia by Aaron Robotham, which we're trying to implement. We haven't quite got it working yet. I was hoping to have it working to show the result in this conference. But the idea is, starting on the left, you compare your blue wisp-affected image to your red image. You use your red image to isolate what all the real sources in your image are, subtract those off. And through some iterative smoothing and masking, you can isolate what's the impact of your wisp is on your image and subtract that off. And this is run on each individual stage 2 output before you get to stacking. And so this, instead of just subtracting off a static single template, this is dynamic, because we're seeing that the wisps are dynamic both in terms of flux and slightly in terms of their shape as well. And so this hopefully will be a way to dynamically remove wisps that's relatively quick without need for implementing a single static template. So this is something that we're going to be investigating further in the future, but I thought I'd mention it in this conference because a lot of people are likely going to be interested in this sort of thing. So where we have 180 square arc minutes, reduced using PMAP 1084. I know Michaela's speaking after me, so I'll just quickly mention this, but not mention it too much. But with NGDeep, we noticed that upgrading from PMAP 0995 to 1084, the flat fielding in the red images was substantially improved, and we got about 0.5 magnitudes in the red images, indicating that flat fielding has definitely vastly improved in 1084, and I encourage people to update to this at least if they haven't already, if they're using NearCam. In terms of where we are going, we're going to hopefully have a series of science papers over the Christmas period and the data release of images and catalogs after that, with a version 2 hopefully following relatively quickly once I've had some time to sit down and focus on the wisping a bit. It reaches a point where there's only so much you can do with the wisping and you need to get some science done. So that's kind of what we're doing this Christmas period. And we'll have more surveys added, such as Primer, Cosmos, and JADES. We have actually already done Able 2744. Cosmos and JADES are running now, as a matter of fact. One sort of sciencey slide at the end. Initial high-Z studies had a sample overlaps of only about 20% to start off with. But this has improved to about 50-60% more recently when you compare high redshift galaxy studies. The consensus is usually on the bright objects, and it's the fainter objects that people are disagreeing on. But this is an example of the updated luminosity function I made yesterday, redshift 10.5, where we see that sort of our samples, redshift 10.5 luminosity function, kind of straddling the middle of all of these studies that have largely been taken with single surveys, indicating that cosmic variance is potentially a problem when analyzing single surveys. And this is the reason why we're trying to combine all of these together. I'm lost track of time a little bit. I may have gone a bit too fast. But the conclusions of this are that deep extragalactic surveys can be largely automated in their reductions over the case of 1 to 5 days. A single Sears pointing takes about 4 hours to go from beginning to end. And something like the new JADES data release has already largely been run in about 4 days. And this is using a 16-core CPU and 250 gig RAM sort of large desktop. It's not a supercomputer by any means. Our product depth consistent with official team reductions within 0.1 magnitudes, which, considering we're a bunch of early career researchers and we're working alongside the JADES team or Sears team, which have official NIRCam members and things, that we think we're doing pretty well with that so far. WISPs remain a sticking point, especially if dithering is pretty small or there's no mosaicing going on to try and counteract or smooth out the wisping. An agreement between high redshift groups on our sample selections are also greatly improving. Started at 20% at launch, and with an improvement of both what high redshift galaxies look like and our understanding of what contaminants look like, this agreement is improving to about 50 or 60% at the minute. So thank you very much. If you have any questions, feel free to poke me in Slack.
Awesome. Thank you very much. That was perfectly clear, so you did not rush through it in that sense. I thought it was excellent. We do have some questions online. You can bring up Slack if you have it handy. We'll discuss. Go ahead and get mic'd up. I guess well, we have some time. So one question from David Grant was, do you think there'd be any advantage to a 1-on-F correction at the group level for your data as opposed to a higher level of processing?
Potentially, yes. I don't think we're really seeing it as. I think we're kind of working our way down in terms of what we consider to be the largely limiting factors at the minute. So we're running where is it? Just sit back to that slide. Whereabouts is it that we're running it? Yeah, the 1/F correction is being run stage 2. I think, yeah, we haven't tried running it earlier than that. It could potentially be better.
Right. Well, let me just suggest let's see what happens in this conference. It's something to think about. There might be some people that will show some results, and maybe that'll give a hint. So I don't know. I don't know what the answer is.
Like I said, like we're open to changing things, and if people have ideas for improvement, I'm all ears for how to get nicer, cleaner images.
Yeah, I think the picky exoplanet people have moved to the group stage because it makes a difference. So maybe we'll see. Maybe we'll see some of that. I'll comment that Mario Gennaro is creating you may have seen a WISP channel. He's in the back there waving his hand for those of you that are here. And so discussion about wispiness, which obviously is a real issue, can happen in that channel. That'll be great. Thank you, Mario. And we'll do one more question. The jump and ramp steps can be run in a multi-processing mode. if you set a parameter from its default value of one core or process or whatever it is to multiple ones. So, and Harry, I don't think I can parse this fast enough. No. Well, we still have a couple minutes actually in the time. So let me try. Well, maybe Nathan, you can read along with me and Harry. He says a few key steps for Sears and NG Deep for background subtraction that have helped a lot. Start with a big ring median filter across each image. Do several steps of source masking using different kernel widths and mask dilation factors to help get both compact faint sources and diffuse wings of brighter sources. Combine the masks from all the different bands, in our case including HST, before doing the background fitting using the unmasked pixels individually for each band. So if you could try that out in the next, before the break, and let us know how that turns out, that would be awesome. So, yeah, anyway, thanks, Harry, for that comment.
I can have a look at that. So thank you very much. I think some of that, the ring median filter, I think is the thing that we don't do. We do source masking, not necessarily different kernel widths, but we do a couple rounds of source masking. I'm just rereading it myself.
So Nathan, what would be great is if you responded to that, trying to lay out the things that you do similarly or exactly the same, or that you don't do, just for the record, basically. That would be awesome. So thanks. All right, let's go on to our first invited speaker.
Can you hear me okay? Is this working? Cool.
Should work the same.
Thanks. Awesome. Thank you. Thank you. First of all, for organizing this, I want to echo what's already been said. It's so exciting to be in a room of everybody, and virtually and in person, talking about all these issues and hearing what everybody's working on. And I've already learned a lot, and I'm very excited. Like, I just want to go back and start working on what we've done for Sears and update it all. So this is really exciting, and thank you for inviting me to talk about some of the work we've done with Sears. I'm going to mostly be talking about Sears, a little bit of NG Deep at the end, and what I'm sort of aiming for in this talk is a really like a laundry list of things we've been looking at, not necessarily going into depth on how we've tried to solve them, but hopefully listing off the approaches that we've taken so that we can talk about them more over the rest of this workshop. None of them, I think, will be a surprise to anyone. I'm sure we're going to hear about all of these in depth all week, but that's good and exciting, and I'm looking forward to it. Starting talking about Sears team. We are, there's a lot of us, and we're sort of spread all over the place, and it's been a wonderful collaboration to be a part of for my first experience as a postdoc. It's been really exciting. Quick summary of our observing modes. We're observing in the EGS field. We have 10 pointings. 4 of them have MIRI as the primary instrument, MIRI imaging. 6 of them have near-spec MSA as the primary. All of those have NearCam in parallel. And 4 of those pointings also do NearCam wide field slitless. I'm going to be focusing on the MIRI and NearCam imaging and the near-spec MSA in this talk. This shows the layouts of those Sears sort of field maps separated by instrument. NearCam is in blue, MIRI's in green, and NearSpec is in red, and I'm going to try to maintain those colors throughout this talk to keep you sort of grounded in where we are. And I mostly want to highlight the work that has primarily gone into reducing these data sets is primarily led by early career scientists, and so it's been a lot of fun, a really good learning experience for all of us, and a lot of time pressure in this like time-pressured environment. So some of these steps we have not had the time to really delve in deep, which is another reason why this workshop is so exciting. So jumping right into NearCam, again, looking at sort of summarizing issues, I want to echo everything Nathan said about WISPs. It's one of our remaining issues. They are sort of low level, but present and hard to remove. And the way that we're removing them currently, which I will talk about in a second, leaves some issues some steps to be desired, or whatever the phrase is. In this, I'm going to try to organize our issues that we're experiencing in categories of like things that we've sort of only partially solved or are not yet solved, things that are basically solved or already part of the pipeline, and then maybe there's a few other things that we would know. And I'm really only going to be talking about the first group, or trying to. And these lists are not going to be exhaustive, but they're the ones that have caused us the most headache recently. So talking about WISPs first, we are doing a template-based subtraction. We are using the most up-to-date templates that are available. We perform this on the count rate images after the detector 1 step. Because of the time variability of the feature, we do try to match the feature, scale it so that it can produce the best. We sort of minimize the variance in our images. If you do image minus template, we scale that template up and down until we find the value that will minimize the variance in the overall image. We do a little bit of processing before we do that scale, apply the flat field so you're doing it on a flat image, mask sources, smooth the template a little bit. But at the end of the day, whatever that scaled value is, we're subtracting the scaled unsmooth template from the original unflat fielded image. So this is done on the count rate images. Here's a schematic of what that process looks like for us. I think it's very similar to what a lot of folks are doing. The upper left shows a mosaic of a near-cam pointing where we haven't done the WISP subtraction. The bottom row shows an image with WISPs, scaling a WISP template by a factor of about 90%. And then the result in the end is what it looks like after you've subtracted off that WISP. These images are smooth, so you can really see the feature popping. And then in the upper right is the corrected mosaic. So it seems to work pretty well. I would say for the most part, it was, like check, good enough for our first data release. But it does have a couple of downsides. Again, this feature is, because it's time varying, we're having a really hard time getting templates that match our images. So we have, this is not super surprising, but in the right, the image that I'm showing is an example where on the right is an image with the WISPs, on the left is after the WISP subtraction, and there are features, part of the WISPs, that remain after the subtraction, and those I think are actually more concerning than having the whole WISP feature in your image, because now you're left with these little tiny things that look compact, and they could look like galaxies, and they could look like real extended features. And so that's actually, to me, like a bigger problem than having the larger WISPs in your images. So I don't like making it worse, but we've made it worse in some aspects of our images. Another problem is those WISP templates. Now you're talking about a WISP feature that covers a portion of the detector, but you're applying it to the full detector. And there are portions of that image now where you've introduced a ton more noise into your image by using the templates. And so we've got a number of ways that we're trying to look at that. One of it is just cut the templates and limit it to just the area around the WISP. It turns out to be a little bit hard to determine where the edges of those WISP features are. And we have, as Nathan mentioned, there is this wonderful approach, this dynamic WISP removal, developed by Robotham et al. Sorry about my pronunciation. And we have also struggled to implement it. We're not having success with it yet. I have a slide at the end describing what some of the struggles that we're having with that, which I can talk about if there's time or interest, but because there's a new WISP channel, and I think we're going to be talking about this all week, I'll leave that maybe for then. 1/f was our next sticking point. Again, mostly a check in the partially solved, but not quite satisfactorily yet. We perform this on the count rate images after detector 1, and we do our correction amplifier by amplifier, which has turned out to be pretty important for us. We measure the pattern, do a little bit, a semi-similar process, mask out sources, subtract a pedestal, apply a flat field, so you're measuring this feature on a flat image. And then we measure the striping pattern using sigma clipped medians. There are certainly more robust ways you could be doing that. This has worked very well for us. We first fit it along rows, and we do that fit amp by amp. So we're fitting it in amp rows. That's what I'm going to call them. And anytime you have too many pixels that are masked in an amp row, you revert to using the median from the full row. Then we do, so first rows, and then we do it along columns. And that allows us to measure what the two patterns are, the horizontal and vertical patterns. And we subtract those patterns from the original unflat fielded image. I think we're finding it very important to do this on the count rate and not on the cal files. And we're also looking at group by group, which I'll talk about in a second. The schematic example of what this correction ends up looking like: uncorrected image on the left, corrected image on the right, and in the middle you can see the two patterns, the horizontal and vertical patterns that we've measured, where those four sort of columns are what you're seeing, the amplifier by amplifier patterns that we've measured. The little, whatever little cutout things show you what the noise in the image looks like before and after the correction. So it is working fairly well, and you know, that's why we have like partially solved. We are finding that we need to do this, that we get a better result when we do this amplifier by amplifier. This is this is an image from one NearCam. This is one NearCam image, all 8 detectors. And you can see in some of them the pattern. You really can see the striping pattern showing up amplifier by amplifier. It's, we have found that it can vary by up to 8% from one amp to another, and maybe in some cases a little bit more. So using the full row we get a better result when we do each amp. So what are some issues with our approach? It definitely is most suitable to sparse fields. It doesn't really work in crowded fields for a number of reasons. That's okay for us. Sears is pretty sparse, so we're happy with that, but it's not generally applicable for that in that sense. One of the downsides is that we do risk cases where we have oversubtraction around bright or extended sources, as shown in this image. It's especially true in images where you've got a source that's close to the size of an amplifier. And so that's sort of an issue. The way we handle that is by changing the threshold we use for how many masked pixels are in a row before you switch to using the full row median. And so that's a parameter that we can tweak when we're doing this process, but that means that our method can require a lot of manual iteration to identify what that best threshold is for each image. And that's honestly like one of the most time-consuming parts of our reduction, is going through and running the 1/f correction. We have very recently started looking at implementing our correction group by group instead of on the count rate images. I think it's very promising for a number of reasons. And one of the interesting, this is very preliminary results, so I'm not sure, I do not understand why this is happening and would love some help understanding it. One of the things that we're finding is that there is sort of there seems to be sort of a global pattern in this noise that is stable up the ramp. So each group has a general overall pattern, but the individual reads are sort of slightly varying in that pattern. So what I'm showing here is the horizontal pattern that we've measured in 9 groups up a ramp. And I would have expected that pattern would change with each group, but it seems to not be. It's varying, so I'm interested in talking about what's going on there and why, and if anyone else is finding that. Another main update that we've made to our process here is using those full tier masks from our mosaics that Harry described when he was talking about the background, where we mask sources with different kernel sizes, so you can get small and large sources all in your masks, and then we do that for every filter, including Hubble, and combine them all into one source mask, blot those masks back, and we're using those as the source masks for our 1/f correction now, and we're getting much cleaner, especially around those big extended sources. So it's progress, but I'm still not fully happy with this. We are also having some struggles with outliers. This is I would call this generally an unsolved problem for us. It's certainly not a major problem, but we have a lot of outliers that are ending up in our images. We find them when we go looking for high redshift galaxies, and we find a huge number of F200 dropouts, and it's just because they're bad pixels in the long wavelength channels. It's a little bit hard for Sears. We have small dithers. We only have 3 exposures, and so doing any type of outlier detection or outlier rejection is a little bit harder. We've tried going about this in a number of ways, and if I'm honest, I just haven't had time to dig into this problem very significantly, so I'm not saying that these don't work. I'm just saying I haven't had a chance to make them work yet. But approaches that we're looking at are, we've taken all of the Sears images and don't register them and just stack them and see which pixels are making it through. we've all sort of, the idea there would be to make our own bad pixel masks, you know, in addition to what is available in the CRDS. We've tried identifying pixels that are flagged like the majority of time in each dither. We've also tried looking at some of the darks that are available from masks and seeing if we can construct things there. And I have not really had time to dig into this in a huge way. Very interested in anyone else who's had success removing really, you know, we're talking about a small number of sources, but they really do show up when you're doing high redshift selections. Okay, so I'm going to switch instruments now, and I'm going to switch over to MIRI and continue our laundry list. I am definitely not an expert on MIRI. This effort is led by Guang Yang, and so these comments are from him, and he's absolutely the best person to ask or discuss more. He couldn't be here in this meeting. He says that our remaining challenges that are really unsolved or only partially solved for MIRI is primarily the flux calibration, and then also just sort of waiting on new flats for the slow readout mode. So let's talk about some of these. So this is a figure from Guang's paper from a few months ago discussing this year's MIRI reduction and comparing the 5.6 and 7.7 micron fluxes to IREX channels 3 and 4. And so this was from an earlier version of the pipeline, I'm not sure which one, an earlier CRDS. And Guang found at the time that the 5.6 micron fluxes were in good agreement with IREX channel 3. 7.7 were a little bit off. But this new PMAP that included an updated flux calibration for MIRI has changed those fluxes, I think made them fainter. And now we're finding that the 5.5 micron fluxes are systematically lower than IREC channel 3. So this is something we're trying to understand. I'm not sure that it's a little bit surprising that they agreed before and now they don't, and we're trying to figure out what's going on. It could be how we're doing our aperture corrections, but something we definitely need to look into and understand a lot better. I mentioned that we still are using, we still don't have flats for the slow readout for the two bluer channels, so we're using, or currently we're just using the fast readout flats. It's okay, it's obviously not ideal, and so hopefully when the team is ready to share those flats, we'll have an improved reduction in that sense. They also have found a spatially dependent background that's present in all bands, and Guang discusses this in his paper, and the way that they address this is Guang has developed a super background algorithm that uses, for a given pointing, it uses all the dithers in that pointing to measure to create a master background and subtract that off. So look for his paper for more information, because I'm not the expert. Jumping right along, now we're switching modes to near spec. This is work that Pablo Arbajaro is leading, and so again, he's the expert, and anything I say is my fault and not his. And so, long list here of remaining challenges that we're still working with on the Sears team, and these are, I've tried to order them, but sort of in perhaps no particular order in terms of pressingness. One example is the bar shadow correction. The current correction, I think, is still based on pre-launch models, and so when we try to run this correction on extended sources, we can still see some of the evidence of those bar shadows in the corrected spectra. So the top one is before, and the bottom one is after, and this is an example of an extended source that we have in one of our slits. The flux calibration is still a problem on near spec that we're encountering. There's Pablo has found deviations of up to 50% when you compare the spectra with photometry. There is this, it's degenerate with the slit losses, and so it makes testing it makes testing what the problem is, whether it's slit losses or the flux calibration, or which portion of those makes it really hard to sort of separate those two effects. What we're doing is fitting a low order polynomial to the flux difference between what we get in the near spec spectrum and the any near cam photometry that we have. The problem is that requires near cam coverage. We do not have near cam coverage for all of the Sears spectra, so this is not a reliable solution. And it also doesn't account for how any slit losses may affect different regions of emission differently that are emitting at different wavelengths. The wavelength dependent slit loss correction makes that a little bit harder. So another one is we've had artifacts or bad pixels, cosmic rays, artifacts in the detector. We've had a huge problem with this in the near-spec spectra, where the pipeline is, we're not able to remove them as successfully by the pipeline as we want, so they end up really affecting, dominating the extracted spectra. So what we did for our data release is we went through and 25 plus Sears team members visually inspected all of our spectra and hand masked every artifact we could find using MOSVIS. And it was pulling teeth, and it was very tedious, and it was very, it was very hard to do. And that means that the next time we re-extract our data, we would have to do that again. So I would love a different solution. But we went through and we tried to mask everything. We tried to mask the really intense, hugely effective artifacts that you can see in the top. And in the bottom right, we also tried to mask, when you just have like a hot pixel that's a little too close to your extraction window. So we tried to be very careful in the spectra that we released in our data release, but love to not have to do that again. We're having a little bit of issue with the master background subtraction. We're not sure if the newest version of the pipeline has a more effective algorithm for this yet, but Pablo said that the master background, it's a little bit unintuitive to set up, and what it used to do, and he's not sure, maybe it doesn't anymore, but it would propagate any of the artifacts that were present in the empty slits you used to build the master background. It would propagate those into your data. So we don't use it, and instead Pablo has developed a custom approach that creates sort of a master background, but just using the slitlets in your slit that don't have sources in them. So this is some figures showing examples of how that works for an extended source where it's a little hard to see on this, but maybe if you look at the PDF later, you can see that the dotted line is just regular knotting, and obviously for extended sources you end up with over-subtraction when you have a source that's included in other or extends into other slitlets. We had I think a little bit of issue with the geometry or WCS in the headers of the spectra. This, I think, we're not sure if this has been fixed yet, but the extension of the slits on the sky seemed to be a little bit off, and what this ended up causing was that the pipeline was extracting spectra at the wrong location when we were processing point sources. So we had to go through manually and define our own 1D extraction limits again, visual inspection by Sears members. So I think this has been solved, but that was an issue that we certainly ran into. We've had a couple of isolated data issues, and this is not a pipeline problem, but I just thought I'd mention them. In both MIRI and NIRCam separately on different exposures, we've had what we've called corrupted jumps, where we encounter a jump not just in a single pixel, but across the whole detector or a whole portion of the detector. So here I'm showing what for MIRI, you've got, I forget which one of these, I think this is the affected by the jump, and this half of the detector was not. And on NIRCam, that's again the 9 groups of one of our exposures where this is the DQ arrays where you can see in the last 2 groups, that's where those jumps occurred. These jumps are not detected by the jump step in the pipeline, and so we've had to go through and find ways to identify them based on sort of the global jump and just manually mask out those areas. We've also had we're having some trouble with persistence. The example on the right is extreme persistence that we had, I think, because one of our observations followed an observation of Jupiter. So that was actually kind of fun to worry about. And what we're doing here is just masking it. But what we haven't figured out yet is how to identify much smaller cases of persistence. We have very small dithers. So trying to look at how something moves, in those 3 dithers, we end up having our sources end up covering the persistence cases. So we're struggling a little bit with that. If you want to learn more about Sears, this slide is in our PDF, just so you can follow us on our website, see our data releases, or check out our papers and find our reduction codes online for MIRI and NIRCam. But now I'm going to go back and make them all into their own pipeline steps. So stay tuned for that. And so I want to switch gears and just take a few minutes to talk about NGDeep. And so got a slide, our huge NGDeep team, which is again another amazing collaboration to be a part of. NGDeep is looking in the HUDF. It's getting ultra deep nearest spectroscopy on the HUDF, and in parallel, it's getting ultra deep NIRCam imaging on the UDF parallel field 2. And I want to talk specifically about the NIRCam imaging. We have the data the observations were split into 2 epochs. We didn't have enough time in our observing window in this past February to get all of it, so we got 1 PA. We're going to come back next February and get the second PA at a 3-degree difference. And Nathan mentioned this, but one of the things we've encountered is that the NG Deep near-cam images were shallower than expected. And I would be very interested in talking to Nathan because this is a problem that we still consider unsolved. We do not understand where it's coming from. The updating to the new flat field certainly helped. It definitely helped a lot in reclaiming some of that depth, but we have not reclaimed all of the depth that we expected. The problem is twofold. One is that the images are shallower than what the ETC predicted. So this is a table showing for filter what the original ETC depth was. These have been updated for the new ETC. And then the depth that we actually measure in mosaics and in parentheses is the difference. So we're talking about, in some cases, that used to be much worse. The F444 used to be like 7/10 of a magnitude shallower. With the new flats, it's actually ever so slightly deeper. So the new flats are certainly helping, but it is not across the board a solved problem. The second piece, the second side of this problem is that there is the MIRI GTO team has images near cam in parallel in the exact same pointing. So we have overlapping near cam images, and in some cases, the images that we have in the same filter, though we have twice the exposure time, are no deeper than their images. So that is telling us this is a problem that we're seeing not just compared to pre-launch predictions or post-launch predictions, but also compared to real data in the same field. This is an image on the right showing the 2, I think it's F115, yes, F115 mosaics. The MIRI GTO team was kind enough to reduce our data and their data in the same, using exactly the same pipeline, exactly the same methods, exactly the same PMAPs. And the 2, it's a little hard to tell here, but just sort of even visually, you can tell that the NG Deep images are noisier, they're shallower, even though we have almost twice as much exposure time in that filter. So this is a concern we're trying to understand. I know a ton of work has been done at the Institute to help us figure out what's going on here, and we're just very much open to discussion and suggestions as we try to figure out what's going on here. There's a lot of possibilities, we're very convinced that, or not very convinced, I think a leading candidate is that there's some fixed pattern noise that's present in reference files that's being introduced. Certainly that was true with the flats. That's been fixed now. But the specifics of the NG Deep exposures and the fact that we're using Deep 8 and the MIRI GTO team is using Deep 8, but we have different numbers of groups and integrations. Like something is different about these exposures that we need to try to understand. It's certainly the case that our dithers are too small. We're highly constrained by the nearest prime, so we can't dither too much or else nearest sources will go off the detector. So it'd be wonderful if we could have larger dithers, but we don't. Could be that we're using Deep 8 with too few groups, in which case learn from our mistakes and maybe best practices moving forward could come out of this. There could be some issues where maybe we're not fitting the ramps as well because we have too few groups. Maybe we're flagging too many pixels or too few pixels in the jump step or the outlier detection step. So there's a lot of things on the table that we're trying to understand, but it's of significant concern. So with that, I'm going to leave up sort of the largest laundry list or the laundry list of our biggest concerning issues for Sears and NG Deep. NG Deep just being the depth problem at this point, and Sears, we're talking about WISPs and 1/F noise and outliers, which we're still working on. Flux calibration for MIRI, flux calibration for near spec, bar shadows, master background, and artifacts. So that's my list of all the sort of struggles that we've had, and really excited to talk to everybody about how you have approached solving these issues. Thanks.
Awesome, thank you very much. So I'm very excited because your talk generated finally a flood of comments in Slack. I apologize to you, but I hope you will spend the time going through and engaging. We have a little bit of time, so I'm just gonna give a preview. If something grabs your attention, just
Oh, okay.
just wave your hand. So some of the questions were about the horizontal versus vertical stripes. Were the vertical stripes people, I mean, horizontal stripes, I think we understand because that's the fast readout direction. Were the vertical ones lower amplitude than the?
So they are lower amplitude, but it's hard. What I haven't done is measure them independently. What we do is we remove the horizontal first and then check the vertical. And so what I haven't done is see what if you just check what the vertical is before you remove the horizontal. Because we're doing that amplifier by amplifier effect, you could see where we may be globally subtracting in a vertical amplifier some of the signal that just belongs to the vertical signal, if that makes sense. I haven't checked, but the way we measure it, it is lower amplitude.
So there was interest in that.
Oh, sorry, I'm not supposed to answer.
No, you
yet. I'm
are.
just-
Actually,
okay.
we're entertaining the crowd a little bit
Great,
with
okay.
some discussion. So we're on the same page here. There was questions about the outliers that were not getting corrected, and were they transients? Were they persistently bad pixels, or both? Were they RC type jumping up and down? Were they blah 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 whatever? So could you maybe give a little more detail about what those things looked like?
All of the above.
Okay. All right. That makes
We
it.
see some of all of it, and again, this is a relatively low percentage-wise. Very few pixels are affected, but they affect our science significantly when they only occur in one of the modules, or one of the channels.
Yeah, so maybe if you could, for my benefit, if you could order them in terms of most annoying, what should we focus on hardest, if you can disentangle the
For the
different-
topics?
No, for the flavor of different.
Oh, I would have to go and let me
if
dig
you
into
don't know,
that
that's
a
fine,
little.
that's
Yeah,
fine.
yeah.
Varun wanted to say he was glad, not the only one troubled by Jupiter persistence. So you have compatriots out there. I want to say Mario created a persistence channel as well, where we can discuss persistence. If you're not savvy about how to join those channels, the best thing is to be just looking in the current session and click on the link, and you'll join that sub channel. For the earlier one, you have to look one level down in the thread where Mario said, should we create one? Then there's a link, and then persistence is in thread. And maybe you could explain again the what was it called? The frames that were the whole anomalous jumps, you call them? Or something?
Yeah, I mean, we're calling them corrupted jumps. We don't.
Corrupted. That's it. It went by a little fast. I wasn't. If you could just explain it one more time.
Yeah, so it's only in a couple of, there's a weird feedback here.
Yeah,
It's only in a couple of, I'll just go back. It's only in a couple of Sears exposures. It happened in only one exposure on NearCam, and it happened in, I think, actually a whole observing set on MIRI. And so and I don't know if they're even the same, I don't even know if the same thing is going on. I think maybe not. But on the NearCam side, what we saw was you step through all the groups, everything is sort of normal. And then at one point in the second to last group, half of the detector experiences a jump. And in the last group, the other half of the detector experiences, a similar jump. And so the jump step of the pipeline wasn't detecting them as jumps. I don't know if it was because it happened to every pixel, or if it was because the actual jump itself was maybe less than it's looking for. But even playing with all the parameters, we weren't able to get the pipeline to detect it, so we just manually did it ourselves. And something similar on the MIRI side, except on the MIRI side, it didn't happen at the end. It happened in the fourth or fifth group. But it still affected half or more of the detector. And so we went through in this case, it was just masking the one group and the group that followed it. In the NearCam side, because it was the end of the ramp, we just masked the whole thing.
I'm Drake Deming from the University of Maryland. I'm interested in the dip in the last group. Is that because you're near saturation, that little dip down at the end?
On the MIRI side, I'm not sure. Guang has an answer for that I don't remember. Oh.
It's known as the last frame effect, and the last
Okay.
frame is flagged automatically in the pipeline.
Okay,
We don't use the last frame in the ramp fit because we're resetting and reading at the same time, and it doesn't work.
Physically, why does that happen?
we reset 2 rows at a time. We get IPC affecting unsampled pixels yet, so they get pulled down because we reset the row below them.
Okay, thank you.
Mistakes were made, yeah.
One more question exchange here with Eddie, and then we'll call it a session.
Right, so I just want to ask about this banded jump you're talking about here. Do you ever see them at the same time in parallel instruments?
No.
You have not seen that?
No,
Okay.
no, 'cause that was so the one on this was taken in, this MIRI was taken in parallel to NearCam that were unaffected. That NearCam was taken in parallel to NearSpec, which was fine, and everything looks fine with those observations.
I've seen one of these before in Nearest. The Nearest team pointed one of these out to me, so
Okay.
I've seen them in other instruments.
Oh, in the same instruments. Mhm. So you're seeing them in you've seen cases where it's in the primary and the parallel instrument at the same time. Okay. Okay. Oh.
It looks like light. It looks like a flash of light in group.
Huh. Okay. This
I wanted to see it parallel in multiple instruments if that was possible.
very cool.
All right.
Thanks, everybody.
Let's thank everybody in the first session. So we have a break now. We will start promptly at 11:15. And people who are in the next session, if you have not uploaded, oh, we're good. We have them all. Thank you, people in the next session.
If I can say something, if you put a comment in Slack, put the name of the person you are asking the question, because there are a lot of questions coming, and if you don't put to whom it is for, it's going to get lost. So put the name that you are asking the questions to, and also the presenters, if you can point in the computer rather than in the screen, so the people that are online can see what you are pointing, that would be great.
Do you know if the tables are set up there, or is that just lunch? The demos or whatever. The
Recording has stopped.
Okay, we'll wait.
Was meant to be a zip file, or is it?
No, I mean,